you get the ROVEX, which is a parameterizable core. You get 2 benchmarks per group. Each group will get different combination of benchmarks. And you have to optimize the core for those 2 benchmarks. The benchmarks which are assigned per group will be also available on Blackboard. I'll put there a document and you can see your group and your benchmarks. Then you can also sneak a bit to see what the others got, right? But this will not help you because you have to do work for your benchmarks. Each group has a different combination and different benchmarks. We didn't have 23, I think there were 23 groups. Not all of them full membership. Some of them are, they have only 2 members. There is a Chinese guy who is solo and who was looking for a group. Are you here? Yes. Did you find the group? Did you send email to the groups and did they answer back? No. Are those guys here in the
but we prefer to work as a
then
team.
talk.
Yeah, we take
Yeah, we want to talk to him.
Then I don't want to force any kind of combination, but I want you to be reactive and to respond and to say, yes, we can, we cannot, whatever, you know,
We answered
it's a fair
actually.
and square game.
Yeah, we answered actually. We answered the email.
You did?
Yeah.
I was not carbon copy, but you know.
Yeah.
And there is another group, which are also 2.
We found the 3rd person.
You found the 3rd person already. Then you have to pair.
Okay, no problem.
You make a triplet. Okay? Then you solve the problem. Just keep me informed about the composition of the groups. Okay? If you didn't send me anything about your reading assignment, please do it ASAP. It is in your own interest because before you get my benediction, you should not start doing the work. I may oppose later on, which may reverse your work and you may actually waste your time. I have the right to veto. Thus far, I did a veto on a proposal. The rest were okay, were a bit too broad, and I suggested to narrow them a bit. Okay? The group which got the veto was looking in things which are interesting for me, but not really relevant for this course. Or somehow, you know, computer arithmetic is part of computer architecture, but we are not dealing with that story in this course. And I don't know if the group is here. Yes, you are here. I'm sorry for you guys, but you have to focus on architecture. I don't have anything personal, you know. You may want it to look in arithmetic in order to please me because you know I'm teaching computer arithmetic and you might have done it as a trick, but it's not working. Okay. Sorry? It is interesting, but it's not exactly in the flavor of the course, and I would like you to study things which are related to what we are talking here about. It's not that it's not interesting what you are looking at. That's not the issue. Okay. Now, today is the last lecture, and this makes me happy, and I'm happy in the same time. It makes me happy because it's the last lecture, and now you can start doing things on your own. Then I did my days, and then you have to continue. From the other point of view, I'm not really happy because what I will tell you today, I don't really like it. Because the conclusion of what I'll tell you today is that somehow things are not as predictable and not as controllable as we think about computers. Changing the paradigm from uniprocessor to multiprocessor is introducing some kind of weird behavior of programs. Then what we perceive is that when you run on your computer a program, the result of that program is always the same for the same input data, which is logical and is correct for not? You don't agree? If you don't agree, okay, you may say it in public. No. Then this is what we expect. This is what we are trained with. When we go to multiprocessors, things may change. And this is because of a contradiction in what we want to achieve. What we want to decouple parts of the application in such a way that they are running faster. But from the other point of view, the applications or the threads, good morning, sir, you will be soloing me quite soon. I was far away. No, I am heavy. Didn't get it. That's okay, don't. Then they are running in parallel, and I get speed up. But from the other point of view, they have to talk to each other. They interact. Now, the interaction will slow down the process. You know, if I'm running fast, which I'm not, but you are running faster than me, you will have to eventually wait for me in order to exchange some data. Then there is not really big time advantage if you run faster and I'm slower and you have to wait for me at all the checkpoints. Now, in order to deal with that problem in one way or another, what we do is we relax some constraints. And we say, you know, whatever used to be the case in serial execution might not be the result of a parallel execution. Because if we make those synchronizations very strict, we lose the performance improvement. And then we may let the programs evolve, and some of the events may not be in the logical order or in the expected order, which may change the output of the program. In some cases, this is acceptable. I mean, if you look for a solution of a problem, let's say you want to solve an NP-complete problem. You know what an NP-complete problem is? All of you, some of you, few of you. I see a head, two heads, maybe. It's a problem which cannot be solved in polynomial time, okay? And usually for those who have heuristics. And what the heuristic will do, will look for a solution which is not exactly, well, you may move, if you want to stay there, it's fine with me, but it's very bad angle. Then, instead of looking for the minimum minimorum in an optimization, what you do with an heuristic is, oh my God, we have beautiful things here. Where is my blue? Not really writing this one. Because I know you like blue, right? It's not that blue. Let's say this is the solution space. In an optimization problem, what I would like to get is this point. But going there may cost me exponential time, and when the problem is large, it's actually not tractable, except if I'm doing quantum computing. Because when I'm doing quantum computing, I may get there into linear time, which is a different story. And I can tell you a bit about that because, you know, today's party is the last lecture, and we can have a bit of fun. Then if I'm doing classical computing, I cannot afford to look for this solution except if the problem is small. And then what I'm doing is I'm doing a heuristic, and let's say the heuristic may bring me here, which might be an acceptable solution, or may bring me to this point, or to this point, or to this point. Or maybe, you know, I may have here another small thing, and I may get trapped in this point. Now, all of those might be acceptable. Then if I deal with such a problem, the fact that, you know, I'm not arriving to the solution which will be obtained by a sequential program is not a problem. But if I'm damaging the calculation and I want, let's say, to check whether or not a bridge will resist for I don't know what kind of pressure, for the train to pass, then I should be careful on this. Now, what do you know about quantum? Quantum physics, quantum mechanics. Did you study that in school? No, just a bit. Then quantum computers also operate in binary. They get binary values, they produce binary values. The power of the quantum computing is on the superposition, on the parallel existence of combinations of 0 and 1 in the same place. Then while you compute, you have this parallelism based on the fact that the binary values, which are inputs, are inside transformed in a superposition of probabilities of having a combination of those. Then while you do the calculation in the quantum fabric, you process enormously parallel amounts of information, because these probabilities are actually real numbers. Now, the problem is that by doing that, you evaluate in parallel a lot of possibilities, and eventually, due to the physics, the ones which are not probable will vanish, they will lose their magnitude. Then you can imagine that there are solutions which are in parallel. Initially, all of them have the same magnitude, which is the probability to be correct. And eventually, by going into the circuit, some of the magnitudes are going to 0, others are remaining still significantly big. I'm just trying to give you an intuition on what's going on. Then it's not really what is physically happening, but this is how we perceive it. Now, at the end of the calculation, I may have errors, and the error probability is large. And I may have, let's say, 2 solutions or 3 solutions which are probable. Then what should I do? What I do is, my problem which I'm trying to solve is NP-complete, it's exponential. But the check for the validity of the solution is linear. Then I am pushing the problem into the quantum fabric. The quantum fabric will provide me a solution, and I check the validity of the solution with a normal algorithm. Let's say I'm trying, it's very famous for quantum computing, the factorization of numbers. I have a huge number and I need to find the factorization with prime numbers. This is for cryptography. Now, finding the numbers is difficult. Checking whether or not they are a solution is simple, because you just multiply them, and if they give you the number, you are in business. If not, you try it again. Now, you may try a couple of times, but still, you will not be exploding in an exponential complexity. In order to diminish the error rate, you also do what is called quantum error correction. Maybe some of you are following the course on electronics for quantum computing. You'll be okay. Then you will see a bit more on what I said. I just try to give you a feeling on what's going on. Then it's still binary, but inside there is a superposition of possibilities, and the solutions are kind of living, growing, and dying. And at the end of the calculation, only the survivors can be, your potential solutions. Now, whether or not this will be a practical implementation, it's a question of technology. And I had a discussion with one of your colleagues, I think yesterday or last week, and he was very skeptical about it. I just want to say that long time ago, when the FET transistor was invented, people were very reluctant, and they say, FET? No, we cannot do that. The bipolar transistor is the right one. We can control it, it's doing good whatever. FET will never happen. FET today is the winning technology. And CMOS is actually dominating the market. Then you can not really foresee the future on this, but probably a big breakthrough will happen if the quantum fabric will become a reality with more qubits, more quantum bits, and then things are in place in industry. There is already a machine which is called, I think, WD Wave or something like that. Something with wave. As I told you, I'm not good with practical things, which is operating on a quantum fabric. It's deployed. You can buy it if you have, I don't know, many millions. There is a company which is selling that. Okay, now we started from a different discussion and we ended up in quantum computing. But that's the beauty of science and technology. You jump from a subject to another one and you can have some fun. Now, then coming back to the story, sometimes the fact that your execution is not following the order of the sequential execution of the program may not be problematic. Other times, it may be problematic. Now, this is actually bringing a problem of complexity from the architecture to the programmer. When you program for your desktop or your laptop, you don't really care about what's going on. You just write whatever you want to obtain, and in the top of that, you have no pain, no regrets when you type float or double and things like that, and the machine will take care of the things. Now, when you do towards parallel programming, you have to be aware about what's going on, and luckily, there are a number of libraries or standards which can help you to keep control of things. It is very much similar, the problem, with the problem of designing an asynchronous system. In logic design, we go for synchronous systems because we keep things under control. There is parallelism in the circuit, but the director of the orchestra, the clock is keeping everybody, in the right tempo. While in an asynchronous design, some blocks may run faster, some blocks may run slower, and if you have a couple of blocks, you can do a mind exercise and evaluate all the possible combinations and see if there is a deadlock, if there are problems. Now, when you want to design a big system, the space of the possibilities which may happen in practice will explode. And then you have a problem. And then you have to limit somehow the freedom of the system. It's the same in programming now in here. You would like to keep the horses which are running fast under certain control, and then you make checkpoints, you enforce checkpoints for that. Now, the more freedom you give to the parallel processor to run, the more performant and the larger the speed up. But you may arrive in problems. Okay? Then you have to find the right compromise. And it is a collaboration here between hardware support for that. In the architecture, you have to have some hardware support to do this. And there are some special instructions which can do that. There are some functions in the system library which can help you to do that. Okay, if you are a bit familiar with Linux, you see that in Linux are threads, and you have some constructions where you have thread synchronization. Yeah. You heard about mutual exclusion, maybe? Okay. Then those things are helping you as a programmer, application programmer, to synchronize the execution in such a way that you don't lose the compass. Then you rely on hardware, library, and at the end of the trophic chain is the application programmer, which has to use those in the proper way. Now, basically, I told you, the story and I can go home. Hmm? Now we'll discuss a bit more about some details. And in order to do that, I have to drop this, drink some coffee. Hmm? Am I allowed to do that? You guys should do that. Okay. I should be allowed at least in the last class. Yeah, what else? I think that something which I forgot. I think for the lab, the assistants, the TAs, would prefer an appointment-based interaction. Then I was personally for the fact that they are available at certain time, you know, twice a week between 10 and 12 or something like that. But in the discussion yesterday with one of the TAs, he said, no, it's better to make appointment. Then you send an email, you make an appointment. And now the other TA is not in Delft this week, but we'll put an announcement on Blackboard what will be the policy to interact with them. Okay, now returning to the multiprocessor, there are essentially two generic structures for multiprocessors. Oops. Gesundheit. Hmm? Sounds good? It's like in German. That's the way Americans will pronounce it. Okay. Then you have this structure where the memory is shared and is not distributed. It's located on a place connected to a bus. Then the backbone, communication backbone, is a bus. Each processor may have a cache, but the main memory is a player which is located in one physical location. And you can have the other one. Where is the other one? No, I'm going in the wrong direction as usual. And you have the other one where the structure is different in the sense that you take the memory and you spread it all over the place. And you have an interconnect, which may be a bus, but most of the time it's a switch or a network, a mesh, whatever, a tree, depending on things. Then what you see, there are two big differences. The communication infrastructure is different. You have a network instead of a bus. And the memory and the IOs are distributed per node. Each processor has a cache, and actually most of the time inside that kind of, what shape is that? It's not a circle.
Eclipse?
Ellipse?
Ellipse.
Okay. I was hoping you will all jump and tell me it's an ellipse. Then inside the ellipse you have a cluster of processors, which means inside of that ellipse you may have a system as the previous one, or just one processor with a cache. The difference between them is that now each cluster or each processor has local memory and local IOs, which are his own, but also shared over the network. And somehow both of those are beautiful and bad from different points of view. The previous one is beautiful because it's more predictable. The bus, it's a common, backbone, and has a certain latency which depends only on the bus access procedure and not on the position of the node in the network. But the bus is just one communication medium, and everybody will be talking there, and you may have problems of overcrowded bus. This one has a different structure. Then you may have interconnects which are particular for some kind of nodes, and they may be faster or slower depending on what you want. And the memory, it's local. Then if you don't look for items which are in other processor memory, you see the main memory or a part of it as being your own. Then you go to the main memory, then you go, while in the previous case, while in this case, whenever I'm going out of the cache, I'm always going on the bus. On this one, sometime I'm going over the communication network. Other times I may find the information in the local memory. Then it depends very much on the capability of the application programmer to do the task allocation and the data layout, whether or not I will interact a lot with my partners. Ideally, I should like not to interact at all. But this is not possible because of the fact that this is a collaborative program. If we don't exchange data, we don't collaborate. And that is a very seldom occasion. Most of the time there are FIFOs, there is interaction between tasks, and then you have to talk to each other. You may say, okay, I will duplicate the data. Then each of the processors will have a local data, a local copy of the full, fledged program. This will work, except that you need to have the results of the processing from another node. Then even if you keep a local copy, which is full copy, you still have to go on the neighbor to get the results of the calculation. Then there is no way to really fully separate, those from each other. And essentially the problems that I told you in the beginning are coming from the memory. The processors, the calculation, it's okay. The fact that you multiply the number of resources, it's fine. You have to be able to use that, and you will see immediately that it's not as pink as we think it might be, but the problems are coming from this memory sharing requirement. Now, there are two ways to do the communication. You can do it with what we call share memory, or we can do it via message passing. Then share memory relates now not to the location of the memory. Then both of the previous schemes can work with shared memory, because the fact that the memory is in one place somewhere, or I have a chunk for my own use, but also for you, and you also each have a chunk for your own use, but also for sharing, it's not making any difference. The difference between the two things is that in the first one, we all see the same memory space. And then if we look for address A1, for you and for me is the same physical address. It might be in my local memory or be in another local memory, but it's the same one. Now, if I'm lucky and I look for one which is close to me, it's fine. If I look at one which you have, I have to get to the location and get it. Now, there are problems with this one, and we'll discuss them later on. And the problems are due to the fact that in order to make things faster, you have to replicate data. And anyway, you have copies in your local cache. And the question is my copy good? Is the latest one? Or there is somebody else who has a better copy of the data, actually an updated one? And I have to know about that, and I have to get access to that in a good way. Now, the other protocol is called message passing, and that's, like sending letters. We don't look in the memory, but if a processor or a process wants to communicate with another process, it sends a message. Then you make, it's a bit, if you want, like on internet. You make a package with the destination, what you want, and the data, and you send it. It may go over the bus, or it may go over a network. But it's personalized communication, and you do not have copies of things in different places. All the things that you share are going via the mail. Send, receive, whatever. Now, you can even, this is a mechanism where you can even do like remote call. Then you can start a process on another processor. You can do also via shared memory, because you activate a location, a certain variable, and you can start there. Both of them, you know, have advantages and disadvantages. Okay. Now, the fact that I'm communicating with my peers will have an implication in performance. And that implication has to be characterized from the point of view of the latency. And another parameter which is important for communication is the bandwidth. How large is the pipe of communication that I can use? How much information I can push there? The bigger the capacity, you know, the faster the communication. But there is a price for that, you know. It will cost you more dollars or euros. And while the bandwidth is limited by the physical requirements, your budget, and I'm not talking mainly about the money, I'm just talking about the energy. Sending information on a bus, or on a bus segment, or on a network segment will cost you energy. You have to switch big lines, you know, long lines. In CMOS, when you switch, remember, you have to charge or discharge a capacitance. When you discharge it, you just throw energy to the sink, which you took before from the power supply. When you charge the line, you get energy from the power supply and you store it in the node. Now, if you charge the output of a gate, which is driving a next gate, the effort will be smaller than when you charge a bus, which is a long line, you know, kilometers in terms of chip dimensions, and then it's a lot of energy which is burned on that communication. Then we have to be careful with the budget. Now, there are tricks in order to hide the latency. Then still use kind of limited resources for communication, but do not suffer from the pain, which is, as usual, by doing things in parallel. You issue something, you don't get stuck waiting for that, you do other things in between, okay? That's something which you should also do in order to better manage your homework and other things, you know, in your studies. Okay. Now in here we have a bit of an overview on what's good and what's bad about shared memory and about message passing. And each of them do have advantages and disadvantages. Now for the shared memory, there is even a kind of standard programming interface which is called OpenMP. Maybe you heard about that, maybe not. As a programmer, you actually rely on calls which are in this library in order to do the synchronization. Then somehow what is behind that library is not visible to you. But the guys which are writing the library, they have to see the architecture, the infrastructure in order to deal with that. Now, message passing is more intuitive. because whenever you have to say something, you write a message. Then as a programmer, you see it in a more natural way of communication. It's explicit communication. But there is an overhead of that because you have to do things. Shared memory, it's simpler in the sense that you write at an address location, which is yours and other people too. And by writing there, which is a normal write, you actually spread the information that you want. It is more convenient, for example, if that information is meant for more users. And by user, I mean other processors. Okay. And while in message passing, you always have to send the information, then you generate traffic to talk with the peers. In shared memory, not all the things are told to the neighbors all the time. Because sometimes you may generate values or numbers in a location which is a shared location in principle, but because you cache it, not all the intermediate results will be told to your neighbors. And this may diminish a bit the traffic. Okay. Now, those are beautiful, complicated calculations. Okay, don't get stressed. The question is, let us look again to Diandal law, which was saying something about the serial code and the parallel code and the speed up. Do you remember that? It was a long time ago. Okay? Now, what this derivation is saying, that if you want a speed up, a large speed up, then if there is no communication whatsoever, and things can run in parallel, with 100 processors, I should be able to run 100 times faster, which we all know by intuition that is not possible due to the interaction. Now, let us see, this is an exercise, what should be the interaction if I want to get a speed up of 80? Then we write Amdahl law, we calculate the speed up, and eventually what we see is that the fraction of sequential code in this, which determines the interaction between the parts in the application, is very small. Then in order to get 80, you have to have 0.25% of the code being sequential, which most likely in practice will not happen. Then you make an investment, but the payback is not really linear. However, there are some strange phenomena. And you may see that when you increase the number of processors, sometimes you get even supralinear improvement. And the reason it's related to another issue, which is the cache. Because you have more processors, there is an aggregated cache which has a larger capacity, and then the miss rate is decreasing, and then the performance is increasing, even though you have communication overhead. Okay? But this will happen when that fraction is not very large. When that fraction is large, no way to get supralinear speedups. Okay. Now, in here you have a table about different kind of multiprocessors, and they give you ideas about the remote memory access time. And you see that the remote access time is quite big. Okay, we speak about 1,000 nanoseconds, which is a lot. And it's a simple calculation which will tell you that if you have a 1 gigahertz processor, which means how big is the clock period? Come on, help me. I don't know how to compute that. Oh. Come on.
1 nanosecond.
Yeah, sure. It took you a lot of time. Then you have a long delay. Huh? Then your cache did a miss, right? The information was on long-term memory. Huh? Then period, it's 1 over frequency. Then you see, it's 1 nanosecond to have, 1 clock cycle, which means local access to your cache most likely, and 1,000 times more, or a couple of 100 times more, the access to the remote memory. This is a lot. And then if you have, let's say, a processor like here with an instruction per cycle of 2, and a latency for the remote access is of 400 nanoseconds, and very few instructions are going to the remote memory, you have an IPC decrease, which is huge. Now, if the percent of the instructions which are going remote is increasing, that IPC is going down to the floor. Then the cost of the communication is actually very big. Then we have application parallelism, which is given. And sometimes it's hidden. As a programmer, you have to bring it up. Compilers can do that, but they are not as creative as we can be. But it's not our natural way of thinking. Then this is something which we can deal with by thinking new algorithms, by rewriting, the code in such a way that you expose more parallelism to the compiler, and the compiler can create a better code for the thing. Now, the other thing which you can do to deal with that is to deal with the remote latency impact. And in order to do that, there are hardware mechanisms like caches, which reduce that, and this is something which the platform architect can decide. And there are things which are software, and again, in here you collaborate with the compiler, and it's about how you map your data and how is your, let's say, the floor planning of your data. If you do it in a careful way, you will minimize the number of remote accesses. Okay. Your last break.